So I'm Bernard. I'm going to be talking about Lunatic. It's a project that I have been working on for the past 3 years. It's a Erlang-inspired runtime for Rust, but you can actually write in any language that compiles down to WebAssembly and run it on top of Lunatic. This talk is going to just be centered around Rust. Actually, the runtime itself, it's written in Rust, but I'm not going to be talking about the implementation details of the runtime. I'm going to be talking how you build application, compile them to WebAssembly, Rust application, and then run them on top of Lunatic, and what properties you can get out of it. To get started, I just wanted to show some code first. It's a bit small. I'm going to just make it a bit bigger. So this is like a hello world application, Rust application, but it's also a hello world Lunatic application. So Lunatic tries to stay really close to the Rust world. So you just use Cargo, the build system, to build the Lunatic application. There's just like a small configuration here, Cargo configuration, where we define the target, compilation target of this project. So we are compiling to WebAssembly, and we are defining a runner as Lunatic. So Cargo has this like built-in notion of runners. And this means if you use Cargo to, for example, Cargo run, it will prefix the compilation target artifact with the runner. So if I just, I'm just going to clear this box. So if you run Cargo run, it compiles everything to WebAssembly, and then you can see it kind of just prefixes here the Lunatic run with the WebAssembly compilation target. So basically it just runs and prints out like what was written in main. So the experience you are getting by writing Lunatic is really close actually to the experience that you get by writing native Rust. Let's go back to the presentation. So most people that use actually Rust, they compile it to native code, and like one of the attractive parts of Rust is that you don't need a runtime, right? So like you don't have a garbage collector, and people usually like this about Rust because it gives them high performance. So why should we introduce like additional layer in between of your application and the operating system? And there are some properties that Lunatic gives you that are kind of really hard to do with native code. So I'm going to be talking today about the concurrency model of Lunatic, the fault tolerance aspects of it, sandboxing, and a bit of distributed compute. So first of all, I would like to start with talking a bit about concurrency. To back off a bit and talk about the difference between parallelism and concurrency, I would define parallelism as something that happens at the exact same time. So if you have two CPU cores and they're executing code at the same time, this is like parallelism. And you're usually limited how parallel you can go by the number of CPU cores you have. But concurrency is more a definition of you having tasks that start at some time, happen at similar times, and kind of finish later. But they don't need to be executing at the same time. You can only have one core executing a bit of one task and then of the other task and then like of another. So you kind of get the perception that they are progressing at the same time, but they are actually physically being not exactly at the same time executed. And modern CPUs are really fast, but modern networking devices are still not as fast as CPUs and also storage devices. That's why it's really good to have like systems that can scale to high concurrency, because you can basically start like thousands of requests, networking requests, and then wait for them to execute all in parallel. And you don't need to have 1,000 of cores, CPU cores. So by default, Rust already provides you two primitives. It provides you like threads and async tasks to do concurrency. Threads are basically provided actually by the operating system. So the scheduling of the threads is done by the operating system kernel, and you as a developer don't have much control over it except picking the right operating system for yourself. But async tasks are a bit different. So also, while like the main problem with concurrency is like you are waiting basically on stuff, and while you are waiting, you need to preserve the execution state of your task or thread. So it's quite a hard problem. CPU core is executing something, it has some registers, it has some stack. So like basically the operating system needs to preserve everything of this like to memory and switch everything out in case of threads. In the case of async tasks, the Rust compiler actually defines a structure that at compile time determines like all the free space that is required for the state to be preserved while the task is waiting. For the Rust compiler to be able to do so, like we need to help it a bit. So we need to define like async functions with await keywords. So those are basically points in code where we say like that we are going to be waiting. So the Rust compiler can create some sort of a state machine that preserves like the execution state while it's progressing the execution. And usually async tasks are much more compact because threads, by default, most operating systems nowadays use 8 megabyte stacks, but the anonymous structure that Rust is compiling in case of async tasks is much more compact and usually in the range of a few kilobytes. And also async tasks are managed in the scheduled in user space, and you can pick your own scheduler. Tokyo, for example, is a popular scheduler for async Rust. So like the third option that Lunatic adds to it that you don't get like with Rust by default is Lunatic processes. They are not like operating system processes. They're really lightweight. They're more like similar to Go routines. Like if you think if you're familiar with Go, or also Erlang processes, that's actually where the name processes comes from. So they are similar in some ways like to both the threads and async tasks. They're similar to threads in a way that they use a virtual stack. So when you're writing Lunatic processes or applications, you don't use async await, the part of Rust. You just write like normal blocking code, like a read function. So you, because we use like virtual threads, you don't need to define this saving state structure up front, like we just keep increasing this virtual stack and adding stuff to it as your task is executing. And they're also managed in user space. We actually in the VM, we use Tokyo for scheduling them. But yeah, so you kind of get like these benefits of async tasks in some way of user space scheduling, and they're a bit more lightweight than threads. And you get like less of the annoying parts with async tasks. For example, async functions cannot be recursive because the compiler would not be able to determine like the exact space you need like to preserve the state if the state could grow infinitely through recursion. So, and also async function cannot be used in traits at the moment, but this might change soon. So like you don't get all this limitation that you have at the moment with async functions. And there is also another big difference between those three, because threads and async tasks, they all live inside of the same heap space. And Lunatic processes, each process gets their own heap. Like so, each of the Lunatic processes gets a heap and a stack separately. So the only way they can communicate with each other, like, is through message passing. And this is a bit of the Erlang architecture that we adopted, like inside of the VM. And many of the properties that I'm going to be talking later about, like, build on top of this property that the heap are separated of each process. I just wanted to show a bit of a demo how it looks to spawn a process in Lunatic. I have here an example prepared, and basically you call, I'm just gonna make this a bit smaller. Basically you call the spawn function, like to spawn something, and you give it a closure so that in this case prints out hello world. And it's fairly simple. It's similar also to threads and async tasks, but the closure is not like an async closure in this case. It has a bit of a funny signature, like with a mailbox and some other parameters that I'm gonna talk a bit about soon. I just wanted to run this to show how it looks. So you see again, I use this cargo run example, like it works like it would with a regular Rust example, but it uses the Lunatic runner to print out hello world. and basically we spawn a child process that prints it out. I have also here a small sleep function because Lunatic VM works in a way when the main process finishes, it shuts it off like the whole VM. So sometimes the main process finishes before the child process has a like time to be scheduled, so it would shut off before printing anything out. So I just sleep for a moment there to give it a chance to print something out. I just wanted also to demonstrate, like modify this code a bit, add a mutable static variable to it to show like this separation of heap property. So I'm just gonna rerun the example again, and you see like we create a global static variable, and then we modify it through unsafe in the main process, and print it out, and it's like 1, but then after we spawn a child and print it again out, like it's again 0. You cannot actually ever access the heap of the main process from the child because they're separated. You cannot even do it through raw pointer dereferencing. It's just like a property. They're physically separated inside of the VM. The only way you can share data is basically by capturing something from the main process. And I also will modify just a bit this code like to demonstrate how you actually share data. So if I try just to capture this Vienna variable inside of the closure, it will not work because the type system is gonna prevent us like to capture it, because again, like to save you some trouble, like we built like the rules around it so you can never actually by mistake share some data. So the compiler will forbid you like to do so. What you need to do is basically explicitly pass the variable through this closure, and that's why these arguments are important. So if I place it here, like you can capture explicitly something and then use it again inside of the closure, and that way it will, it should just work. It prints out Hello Vienna. So basically, I just wanted here to demonstrate like some of the properties around processes. Like they're fairly simple, and each process also gets a mailbox. A mailbox is just a way to pull out messages that you send out to the process. So I could create like a variable. Let's call it P here. And assign it like to the process, and then I could like send something to p.send, and it would basically be sent into the mailbox of the process, and then the child process could pull it out of the mailbox. All right, let's continue. So this idea of sending processes, like to sending messages to a process, it's quite common. Like you usually hold some state inside of a process, and then you send messages, you modify the state, or you query the state and get like something back in, like as a response. And in this case, like we also build a small abstraction in Lunatic, like it's called the abstract process. It can be implemented as a trait, but here I'm using a macro to make it a bit simpler and provide some additional ergonomics around it. So for example, we define like a process state called server, and it has just like a integer, unsigned integer, 32-bit state, and it has like a few lifecycle methods. So the init method is called when the process is started, and it can bootstrap its own state, and it can also receive some configuration from the parent. And then we can also define handlers that just look like regular methods. So basically, when you send an add message with a specific value, it will add it to the state. And the request is basically a message and a response that you receive back from it. But when you're writing in this programming model, it seems more like you're basically doing function calls. And the terminate method is called if you call the shutdown function on the server in this case. So basically you start a server by just writing like server start, and you need to unwrap it because there could be a failure during the init process that's going to be returned as a result, or if you even panic inside of the init method, like this is going to be returned as an error like from the start function, and then you send messages to it by just calling as if you were like calling methods in Lunatic, and this makes like some of the abstractions way easier like to do. So I'm not going to run this example, but it's fairly simple. It just prints the state of 0 when it starts up because we define it here as 0, and then like later it prints out the state as 4 because we added 2 times something to it. So basically, like it seems a bit like strange and limiting that we introduce this like separation of all the heaps inside of processes, but all of the other properties, as I mentioned, of Lunatic build on top of it to create like some really cool abstractions. And one of those ideas, like taken also from Erlang, is the fault tolerance model of Lunatic, and it's based on this idea that if you start like a new process, it usually has a fresh state and it's working correctly, but after some time, like it's gonna get into a state that the developer did not predict, and then the best thing kind of to do is like Erlang also calls it let it crash philosophy. So you basically just let the process crash and restart it again, and then when you are starting from a new fresh state, you can you are sure that the application is correct, like that the process has a correct state when it's starting from the beginning. So, and there is abstraction built around it in Erlang and also in Lunatic is the supervisor. So basically you need to buy in a bit into this worldview of Lunatic and Erlang to construct your applications around supervisors and supervision trees. So you separate your application into independent processes that send messages with each other, but you express dependencies between the processes with a supervisor. So you can say like if one of the worker crashes, you should restart also like all other children or like just the worker. And you can have interval of restarts, like after 5 restarts, also crash the supervisor and propagate the error like upwards. So at the end, like sometimes you cannot recover from some error if there is like a networking loss, like you need to ping a human, eventually you're gonna propagate and your application is gonna crash. But in most cases, you can get really far just by restarting parts of your application and keeping the system alive, while also in the presence of failure. And I'm just gonna also display, like show you a bit of code, like how supervisors are defined. Like this is basically the same server we had before. It just has like an additional like method handling panics. When you send a panic message, it just like panics and fails. And this is a supervisor. Supervisors are usually defined as structures that don't have any data and that implement the supervisor trait. So this supervisor has 2 children, like both are the server, and it defines a strategy 1 for 1. This means like if one of them crashes, restart it again, but it doesn't matter, like don't do anything to the other one. And you can also submit like some initial arguments to the supervisor, or in this case, I also register it under the name server1, the first supervisor. So Lunatic also has an internal registry where you can name some processes. And in this case, I named the first server1 that started by the supervisor. And you can later look up from anywhere in your application, from any other process, like through this lookup method. the process, and I have here just like a server one function, helper function that looks up like the process with the type server and name server one. And yeah, and this works as you would expect it. Like when you start the supervisor, it's gonna start both of the children. And then if you look up like the supervisor and print out the state, it's again gonna progress until 4. If we call panic, it will crash, but the supervisor is gonna restart it again, and then it's gonna start again from the state 0. And again, we can like progress it until 4. So this is a fairly simple example and like a bit trivial, so it doesn't really make like doesn't show like all the characteristics of system built upon this like idea, but like in fairly complicated systems, it's like really useful to be able to have like part of your system fail and but the rest of the system not be affected by the issue. And again, like this property comes like from the fact that one process can fail, but it will not mess up anything inside of other processes. You're not going to have a mutex that's locked or anything because no memory is shared. So it's kind of safe like to restart something, but not. You don't need to care like what in what state other processes are because of this like strict separation. Yeah.
So in your example, you are panicking explicitly.
Mm-hmm.
What if the server dies during the call to state or during the call to
Mm-hmm.
does the runtime automatically resend the message to a restarted?
No, it doesn't do. Like there is, so basically state is like a send and receive. So you're gonna send a message, but like you're not gonna get a reply back from the server. So it's gonna probably hang. So there is actually like a function here that you would do like, I think it's called like with timeout, like, oh, sorry. With, I'm not sure. Uh, sorry. Yep. It's not auto-completing it, and I was thinking, yeah, with timeout. So basically, you could specify a timeout how long you would wait on the response back because it could fail any. Usually, we just provide low-level primitives at this level, library level, so you don't get like automatic resends or anything. You would need to implement this on a higher level for yourself. But yeah, this is like the idea behind the supervisors. And let's go to the next point. And this is also a really interesting concept. Until now, like you kind of could fake everything with async Rust or threads. You could use channels and messages. You could kind of build some supervisor, even abstractions in some way. But like the next part, like that I'm going to talk about it, like sandboxing, it's kind of really hard to do without like virtual machine in between, like sitting your application and the operating system. And if you think about it, like there's like a bit of a graphic here, like of each of these like cubes on the top as processes, like they're calling through the virtual machine, like to the operating system, but the virtual machine has all the control what syscalls are allowed. So you can spawn a process and say like this process is not allowed to make any networking request. It cannot, like it can only open certain files. You can even give memory limitations. Say, for example, if you model a web server and each request is a new process, you can say like this request can only execute 100 million of WebAssembly instructions and use 5 megabytes at max. And if it like exceeds this limit, it will just crash. So you kind of can build really interesting safe abstraction on top of it. And this is thanks to being built on top of WebAssembly, because WebAssembly was made to run in the browser. So like the sandboxing capabilities around it are really, really good. Like nobody should be able to like mess up your PC by just visiting a website. So we make use of it. And so you can provide capabilities to each individual process, like the granularity level of it is like a process boundary. So this is also a really cool limitation that would be really hard to do with native code. And I have just like also a code example, how it looks basically when you sandbox something. So in this example, I'm creating a process configuration and adding an environment variable. And here, as you see, like I'm just using the standard environment vars standard library printout, like from Rust. But this child process is going to see different environment variables, only the ones that I provided here, not the ones provided by the operating system. And I will just run this example to show how it looks. So basically, it just prints out, spawns a child process and prints out the environment variable. But if we, for example, printed the environment variables from the main process gets all like the system environment variables, like, so it should display like everything. And I believe it's a bunch of them like on my operating system. So like you can basically limit all the syscalls inside of a process that you're spawning. And not only this, you can also limit like memory usage. For example, I'm here allocating a vector that has like, I think it's like 40 megabytes, like, because it uses U32, I think, as the default type, and I'm allocating 10 million elements of it. And if I can also have a config that basically sets the maximum limit, max memory. And I'm just going to limit it actually to this value. And if I try to run this, the process is going to fail because the memory allocation, the child process is not able to allocate the memory. And then we see here also like a printout of the VM that one of the processes failed. So you can do also compute limitation, what's also really cool because you can basically limit the number of instructions the VM is going to execute before like the process fails. So you can do really interesting abstractions. And we expose all the internals we use. Yeah.
In this case, what is the error handling story? Like, you have a max memory limit and your spawn process crashes because it exceeds this limit. Do you get a stack trace at this point? How can you actually capture this?
This is basically like what Rust prints out, like when you run out of memory. So like how it works actually, it's the Rust vector function panics while it's executing this instruction. So the process will fail. You could, if you add it to a supervisor, you could restart it in that case or do something else. There is also an idea of process linking in Lunatic, like you can link to processes that depend on each other. So if one of them fails, the other like link gets notified or crashes also. So you would need to build some abstractions, but it really depends because like you don't have much control here what Rust is gonna like do the standard library in case of the vector. Basically, if yeah, you can also like, because when you call, I think malloc, this will actually not fail. It will just return like no memory. So if you use a library that's like more aware of memory allocation, you kind of get also an error and can handle it and deal with the smaller memory space. But it really depends like on the underlying API you're calling. So in this case, it just crashes. So you would need to depend either on a supervisor or some other abstractions to handle it. But yeah, so this is the sandboxing story of it. And the last part that's left is the distributed part, and this is actually like my favorite part of Lunatic, and I think it's really cool. So basically, Lunatic lets you define multiple nodes and link them together into like a cluster, and then you can just spawn processes on each of them. And because like already we are starting from this programming model where each process has a separate heap, so you don't actually need to do anything special because like you don't really care if your heap lives on the same machine or another machine, and the whole application was built around this notion of message passing, but now the messages don't go through the main memory, they just go through a network. And also because we are working with WebAssembly, so you can have different types of nodes, like you can run a Windows machine with a different CPU architecture, but you can spawn just a closure from a Linux machine, and it's going to be just in time compiled to the right CPU architecture and executed there. So you can have a mixture, heterogeneous like network, and you can build really cool abstractions even around this. We use like Quick as the protocol, like to encrypt all the connections. It's based on UDP between the nodes. And yeah, I'm just gonna show like a small also example how this looks like in practice. And for this to be able to work, I need like a few other nodes running. So you can, first of all, you need the a control node for all these other nodes to discover each other. Like, but once the control node is used like to for the first time connection, but then later all the nodes connect between each other. So like the messages don't go like through one node. So basically, I just change also the runner. Like, so we start locally a node when I run like cargo run example 5, in this case distributed. And the distributed like example also does something similar to the first example we saw in this presentation. It just like spawns a closure, but instead of using spawn, we are doing like a spawn node, and then we just use the nodes function in the distributed module to get all nodes and like just spawn this closure on all existing nodes. And like because we're executing also on one node, this example, it prints out, and like this is like the other node that we had in the system. It also like spawns like a closure and then prints out hello world on it. But this could also be like a server running somewhere else. Like it works like anywhere where you have a networking connection and UDP available. So yeah, that's like that's it like from the presentation. I have also like a cool demo that I just wanted to show a bit. Like it's a more fuller application built on top of Lunatic, because we have also a web framework. It's called sub-millisecond, built on top of Lunatic, and it allows you to build like applications that are all in Rust, but you don't need to write any front-end code, JavaScript, but we keep kind of all the state on the back end and modify it. Like you can modify it from the front end and also from the back end. And I have built a small chat application, and this is going to be kind of really hard to show on this like huge font, but I'm going to do my best to do it. Like I'm just going to copy this URL and go to open it in a browser, and maybe open another browser here next to it. And so it's like basically a chat application. It's only Rust code, so we didn't need to write any JavaScript for it. And I'm just gonna write hello, and it just appears in both windows. So it's kind of multiplayer, already a bit more complex example. And how it works, it's fairly straightforward. In the main function here of the application, we are starting a few processes. The broadcaster process that will just like all other clients just subscribe to it, and then it broadcasts a message to all of them. And the users process that just assigns, if you saw it like in the example, it's basically each of them has a kind of different username and like a different color scheme around the window. So it kind of pops the last color, and everybody gets a unique color. And if you look at these processes, they're just like simple abstract processes in Lunatic. Like in this case, you just like use the request, and we pop like one of the existing, and once you run out, like it will just fail the process. So we don't do any message, like any error handling here, just like for demo purposes. And the broadcaster, you can also subscribe to it, and then it pushes like to all the existing clients your message. And the main part here is the live view aspect of it. So we define a process like that lives on the server, and it renders the HTML. And basically it has some state, like, and it contains all the messages, and we kind of just loop through all the messages and print them out. And if we hit enter or like submit, it sends a message submit to itself. And at the end, we are kind of handling two messages. We are handling the submit and also the broadcast message. And in case of the broadcast, like once a new message arrives, we just push it to the state, the message state, like. And in this case, once we modify the state, the re-render method reruns automatically and changes, like re-renders the new state and just sends a diff of the HTML that changed to the front end. So it's kind of really optimized, like to minimize the traffic between the backend and the front end. So you kind of can write as you noticed here, like this submit handler is handling messages that are coming from the front end, like what the user is typing in the browser, but like these broadcast messages are coming from other processes that live like on the same machine, but they could also be distributed, like everything would just work transparently like in Lunatic, and it's like this is a nice part of it, because once you kind of have this idea of it, that everything has a separate heap, it doesn't really matter where things live, like everything is done through message passing. Yeah, this is a bit of a more complicated, so you can already build like cool stuff at Lunatic. I would encourage you to try it out and join our Discord server. Like we have already, I think, over 800 users, so like it's a fairly big community around it. Yeah, that's everything. Thanks. I think I have some time for questions. Yeah.
If I understand correctly, in this web browser demo, the web browser is communicating through something WebSocket with the server, but all the actual code is running on the server and just communicating possibly between many servers. Given this is running in WebAssembly and the quick serialization is probably easily exchanged with something, say WebSockets, um, why do you need that server? Couldn't you just send the same WebAssembly down there with just different transport, no way to execute own system calls, because on that node there are no system calls anyway. So in other words, if I have a computationally bound problem and a website that talks about it, can everyone who opens that website please join my cluster of computing nodes because they are being sent that task?
Yeah, we could actually do something like this, and we have been experimenting with it, because we're already using WebAssembly, as you mentioned. Like we can run the same code inside of the browsers and just communicate through messages. There is just a small like issue at the moment. Like I have a demo that kind of works in Chrome, but for the Lunatic API to work, because we use virtual stacks on the backend to execute the WebAssembly, and you only have in Chrome like actually this virtual stacks, like where you spawn like a process, because you cannot actually use from WebAssembly like call into a JavaScript async function, like for example networking send, and block there, like, and this kind of defeats like all of our libraries that expect like to block on those calls. So like we could build something, and this would actually be the next step. We're also thinking about some use cases with offline use cases, basically, where you kind of have like the whole server live inside of your browser, because like we kind of can just transparently move it to your browser, and then you get like part of your application that doesn't need to be online running locally in your browser. And we think it's kind of like there's like a huge area to be explored there. So yeah. Yeah. Sure, sure. Mm. We use Wasm-Time. In the beginning, we used like our own stuff, but eventually Wasm-Time kind of like integrated all the things we needed, and now we're just using Wasm-Time, and it's the, like I would say, most popular and well supported at the moment. Yeah, we provide our own library, and as you can say, like we have this like Lunatic library, and we have like a networking namespace, so you can it's kind of compatible with the Rust standard library, so like you get TCP streams, and you can listen like on TCP connections, and everything is built on top of it. Once it gets like standardized inside of ASI or something, we can just like switch to the standard library at the moment. Yeah, no, no. If you're depending on some library, but it works with anything that implements read and write streams. Like, so if you have the traits like read and write, if you have some library that works with them, it automatically works with anything. But yeah, many also libraries depend on the async read and write, like that's like Tokyo specific. So there are a few issues. Like it's not like that everything will work inside. Yep. it's serialized, like, and you can actually define the serialization format as a type, like when you're spawning a process. We use Bing code by default, like, so that's why you didn't see it in any of the examples. So it's kind of serializes and copies like to the other, because sometimes it also travels over the network, so we need to do some serialization and then deserialization on the other side. It's basically like it's copied inside of like from one heap space into another through a buffer, like. Yeah, in the runtime. The runtime manages. You cannot like access the other memory from inside of one process because. Yeah. Yeah.
So you mentioned for the distributed example, you have like a control node. What happens if during runtime the control node dies?
I have like here also like some of other developers that work on Lunatic, and they work on the distributed part. And our idea is like the control node at the moment is fairly simple, like, and it just basically keeps the state of all of the other nodes. But we want to allow you also in the future to have like a more distributed like control nodes. So you have a raft or some other consensus algorithm between the nodes. So if one of the control node fails, like you can just like rely on another one or bring it back on. But at the moment, if one of them like goes down, you're a bit screwed. Awesome. Thanks.